Swayam Prabha. Digital India. Educated India.
Welcome back. Today we will start module 3, collection of water, and in lecture 11 we will start with rainfall, runoff and groundwater. So, the different concepts that would be covered in this lecture are hydrologic cycle of water, precipitation and runoff, measurement of rainfall, measurement of runoff and runoff determination. So, when we talk about the hydrologic cycle of water, we have all studied this in our schools, and we know that this refers to the continuous changing of both the state of water and the movement of water both on, above and below the surface of the earth, right. So, what it means is whenever we have due to sun's heat, the water evaporates. So, it changes state, it changes from liquid to vapor, and then once it goes up, then it gradually expands because of low pressure over in the upper layers, and then it condenses and condensation takes place, and eventually when the dew point is when there is dew point, and then precipitation happens, and the water that goes up again comes down in form of either rain or snow. So, this is the hydrologic cycle of water which goes on continuously. So, there is both change of state as well as movement of water, and once the water falls back on the earth, it again moves in different ways. For example, some of it percolates or gets inside the earth's surface and then moves within the earth's surface, and so and also some of it moves above the earth's surface, right, and then it goes towards the different rivers, streams and the different water bodies from where it evaporates again, right, and the evaporation also takes place from the soil layers as well. So, this entire process is the hydrologic cycle of water. So, this goes on continuously. And then when we talk about this precipitation and runoff, we know that evaporated water is returned to the earth both in form of either rain or snow, and this is known as precipitation. And this precipitation, even though it involves both rain and snow, but we usually take them separately, we measure them separately because of they are in different states. And for example, when rainwater is usually comes down at precipitation, sometimes we directly use rainwater for certain purposes, but it is actually not, it is not actually, it should not be used directly. Before, why? Because rainwater is sought, which is actually good, it helps you cleaning the clothes and all, but it is also a little bit corrosive. Why? Because it has got a low pH value and low alkalinity, that means it is a bit acidic in nature. So, it is better not to use rainwater directly, and there has to be some form of treatment because before we can use it for some potable use. Then when rainfall, when precipitation happens, that means we talk about rainfall from now onwards, we are not talking about snow, then most of the rainfall of course, so also snow as well, falls on the different, in an urban area, falls on the different surfaces. That means there are paved surfaces, there are green surfaces, and most of it falls on the buildings as well, right, and many of it, much of it falls on the buildings, on the rooftops. So, the snow or the rainfall that falls on the rooftop usually is drained from the roof by means of rainwater pipes, and then this water directly goes into the drainage network, and it is drained into the through the drainage network of the city, either or the sewerage network. The water actually is transported towards the treatment plants or to the final disposal points, which could be streams or rivers and so on. So, this rainfall is already going through, entering into the pipelines or the drainage channels, and cannot be and does not generate any kind of runoff, right. So, once the rainfall falls on the ground, and then once it it comes to the ground directly, and then it actually flows over the ground, and then it is actually, we call it a runoff, right. Now, when rain falls on the ground, depending on the kind of surface it falls on, some of it, if it's a surface where it has got adequate where it is impervious, it is not impervious, in that case rain actually gets a little bit infiltrates inside the ground itself, right. So, even in paved surfaces also, some amount of rain also gets infiltrates inside those paved surfaces and eventually reaches the ground. So, rainfall reaches ground, once it reaches the ground, it starts to infiltrate, and that means it starts entering into the soil, and then once it enters into the soil, it starts moving inside the soil. So, some amount of rain, some amount of this rainfall can move below the surface as well, and some amount of rainfall moves above the surface in form of runoff. So, this infiltration capacity refers to the maximum rate at which soil in a given state can actually absorb water. So, depending on the infiltration capacity, certain percentage of the rainfall will be getting inside the ground, and certain percent remains above ground, and then it actually moves on. Now, once the amount of rainfall that actually remains above the ground, so some amount, the first thing that it does is it fills up all the different smaller holes or pores that are around, and so this is called a depression storage. That means all the smaller undulations and all are filled, and then whatever amount of water is detained, this starts flowing in form of a laminar flow. So, it flows in form of a lamina, and it flows over the surface, and this accumulated water on the surface eventually, once it flows over land, then eventually reaches the streams and river, and this is known as the surface runoff. But as I was telling you, there is also a subsurface runoff. That means the water that flows just below the surface and then also moves in the direction of the streams, and eventually gets out and moves gets out into the stream and contributes to the water in the stream. So, this is the subsurface runoff which also happens, but surface runoff is the one which concerns us at this point. So, this surface runoff is the one which actually, if we cannot control it, it will lead to floods, it would lead to urban floods and so on, and we actually want to control this particular flow by either taking them into certain drainage channels or determining the size of the drainage channels appropriate to take this flow and so on. So, that is how we should actually manage the different kinds of the amount of runoff that is generated in urban areas. But first of all, before we again go into determining how much is the runoff, we first need to understand how much is the rainfall. So, we need to measure the rainfall. So, how do we measure rainfall? The total amount of rainfall falling on the earth in a given time period is expressed as the depth to which it would accumulate on the horizontal projection of the earth's surface, assuming no losses by evaporation or runoff. That means, what we do is we assume of course, earth is round, but we assume a horizontal surface, and we take a unit area and we determine how much amount of rainfall has happened in terms of the height of the water that is accumulated over that particular surface, right. So, that is how we measure the rainfall. So, and the one thing that we need to be careful about is whenever rainfall happens, parallelly there is also evaporation, and then there is some amount of water that goes away. So, we should consider that no evaporation is happening, no runoff is being is generated from this particular point. The entire water is measured as the total amount of water that is falling as rain. Okay. And the other thing is, we also should measure snow and ice separately, because these are the matter is in different state, water is in different state, one is in liquid form, one is in in the snow form. So, in that particular case, we cannot measure them together. So, that means it has to be measured separately. So, how do we measure rainfall? So, the rainfall is measured in millimeters. That is, I was telling you that there is on a horizontal projection of earth's surface, what is the height of water that accumulates on a unit area. So, this unit area is, this height is measured in millimeter. So, whenever we measure rainfall, it is in millimeter, and the equipment or the instrument that we use to measure a rainfall are called rain gauges. So, rain gauges are horizontal surface apertures of known area for collecting rain and then measuring it at regular intervals. So, it's we know that it's a sort of a cylinder where we allow the water to accumulate, and we know the area of the cylinder. So, we exactly know how much based on the height of the cylinder, height of the rainfall that has accumulated within the cylinder, what is the total amount of rainfall that is generated within that time period. So, and it is measured at regular intervals. Why? So that we can measure the intensity of rainfall at different time periods. So, how much rainfall happened at different time periods, right? So, that is why it is measured for different at regular intervals as well. Now, there are two types of rain gauges. One is a non-recording type rain gauge and other is a recording type rain gauge. So, as you can understand from the term non-recording itself, we understand that it is more or less there is it's sort of a static measure, right. So, what it means is these are used for collecting rains, which is then measured using graduated cylinders representing the rainfall volume in millimeter. So, it is basically just a container which measures the rain, and then we have this measured graduated cylinders. When the content of the container when put into this graduated cylinder, it will give us that actual height of rainfall in millimeters. So, and why it is graduated? Because we have already measured that what volume reaches what height and accordingly what the rainfall would be, right. So, we already have done that earlier. So, that is why we have graduated the cylinders. We just pour the content of the stored rainwater and measure what is the height it reaches, and accordingly say this is the amount of rainfall in millimeters. Or it could be a recording type rain gauge. So, again from the term itself you can understand it is a little bit dynamic, it is not static. There we are able to give automatic readings for different time periods, and we can also measure the variation of intensity of rainfall. So, that means during different time periods, if we are able to measure how much rainfall happens, so automatically we are measuring the intensity of rainfall at different time periods. So, let us look at two of these figures that is given over here. So, the first figure actually shows a standard rain gauge, which is a non-recording type rain gauge, and as you can see over here, it is a cylinder. As this is this container, as you can, this is a container that over here that you can see, and it has got a funnel at the top. So, whatever rainfall falls within this particular area, which is around 200 centimeter squares, or it could be 100 centimeter squares cylinder as well, and we actually collect that amount of rainfall. The rainfall is collected into this particular container, and then what we do is we actually so this is something around 60 cm high and 20 cm diameter cylinder with a funnel at the top, and height of water is measured using a measuring stick. So, that means we put a measuring stick inside, and the measuring stick is graduated. That means we have given that millimeter based on that particular height of water within that particular cylinder. It will show us exactly how much millimeter of rainfall has happened, because we have already calibrated or graduated that particular cylinder. Okay. And so, it can measure up to an accuracy level of 0.1 mm. So, this is the standard rain gauge. So, there is nothing more moving parts. We just collect the rainfall, and we using a graduated stick, we actually measure at what height the water has being accumulated, and that gives us an idea about what is the rainfall for that particular area. And this standard rain gauges are used, this could be set up in any points at any locations, and we can actually measure what kind of rainfall is happening, but it has to be measured at certain intervals. Otherwise, you would not be able to understand what is if there is change in intensity of rainfall. Similarly, we have got other kinds of rain gauges which are recording type. There are several kinds. The image actually shows of a float type of rain gauge, and as you can see over here, it is again a container like this one, this box, this cylinder, and there is a funnel over here as well. So, whatever rain falls on the funnel gets inside, and this float gradually goes up, and there is this is a cylinder over here, this one, and this cylinder rotates, and this has got a graph paper attached to it, and maybe this for representation it is given like that. It is fixed into the cylinder rotates, and this arm actually, because of the float, it goes up, and there is a drawing there is a point which a recording pane fixed over here, which as the float goes rises up, it will gradually move up, and because this cylinder is also rotating, you will see that there is a change in the height of this line, and you can understand what is the intensity of rainfall. right? So, following this graph, we can determine how the intensity is changing during different time periods. So, once the water reaches a certain height within this particular container, then because of this siphon effect, it gets out, the entire water goes out, and then again we water until this level goes out, and then again we start recording the next time period, right? So, in this way we keep on recording, and this is an automatic system. Just to summarize, this is a rotating drum with a graph paper is fixed. Recording pen moves with a float and records on this particular graph, and cumulative rainfall is recorded, right? So, this is how you can automatically record the rainfall at different time periods. So, in addition to float type rain gauges, there is also other kinds of rain gauges, such as the tipping bucket type and the weighing device type. So, as you can understand, in tipping bucket type, sort of a container is filled, and once it is full, it tips, it gives away the liquid, and again it comes back and again gets filled. So, the number of time it gets filled and emptied, that actually records the total amount of rainfall during different time periods, right? Similarly, weighing device type also depends on the weight of the rainfall and so on. So, this is how we can measure the amount of rainfall that falls in a particular urban area, or for any weather station or any area, you can measure what is the type of rainfall. Now, once we know the rainfall at a particular point at a weather station, like for example, in this particular drawing, you can see this, these are the points where the rainfall is measured. Now, I want to determine what is the total amount of rainfall that happens in a particular area. Now, in this particular area, there could be several rain gauges, and like over here, as we have fixed over here, but the point is, the rainfall is not uniform all throughout during a certain rainfall event. At different points we will find different amount of rain that has happened. So, you have seen that at one point in an area there is rainfall, the just area beside that there is no rainfall, right. So, that means there is differences in both the intensity of rainfall as well as the event of rainfall that also may happen in one area, in another area it may not happen. But suppose I am designing a drainage network for this entire area, this overall area, right. So, that means this entire, because of the slope of this area has been made into one zone, and this drainage network has to be designed. So, I need to understand during certain time periods what amount of rainfall happens, and it is measured by these rain gauges for different areas. So, what I require is to measure the average rainfall for this particular area. So, how do I determine the average rainfall? So, that means I can take the rainfall readings of each of these particular weather stations and divide that whatever millimeter of rain that has happened in those weather stations. I take all those readings, divide by the number of weather stations, I get the average. We could do that, but actually it would be wrong. Why? Because we do not know exactly how much area is being represented by this particular weather station. So, the method to determine what amount of area is represented by this weather station, we follow a method which is called the Thiessen method, and this Thiessen method actually refers to creation of this polygons around the weather station, and in such a way so that there are continuous polygons and there is no area which is unrepresented. That means each area there is we can assign a weather station for that particular area. I will tell you the method. Before that, just to summarize, we need to determine the mean annual rainfall for a particular area, that is understood. So, for this particular point, we can determine mean annual rainfall by adding all the different rainfall events that has happened, total amount of rain I can determine for that area. And if I want to determine mean annual per day, we can divide it by the number of days for that particular area, or for a particular season we can also divide by that particular number of days. And then using this mean annual rainfall, we have to design different kind of infrastructure that is required. Infrastructure means, in this case, what kind of drains, what kind of drainage channels, and all these things has to be determined. So, for design, we usually look into the data of rainfall for the last 20-25 years, and sometimes even more. So, why? Because rainfall does not happen uniformly every year. Some year it is high, some year it is low. So, this amount varies, and sometimes there is huge, the variation is pretty big, right. So, we take an average of around 25-30 years, and we try to find out that what have been the intensity of rainfall during this period, and we take the maximum values during this period to understand that this kind of rainfall event is possible. And if we don't take that value, then what happens? If I design my infrastructure like drainage channels, detention basin based on a lower value, then during the actual event there may be chance of flooding and so on. So we need to determine our the rainfall that has happened during the last the extreme events that has happened during the last 30 years, and then based on that we will design our infrastructure. So this is one, and sometimes we also try to determine areas which could be assigned a similar kind of rainfall, and that is why we have this ISO lines, ISO heights these are called. So all lines of equal rainfall based on this point data could be connected, and we can draw this sort of rainfall contours, you can say. This is called ISO heights. Okay. So this kind of we can also draw this kind of lines as well. So to determine average rainfall in a particular catchment area, which is required to design the drainage infrastructure for this particular zone or catchment, then we first of all we have learned how to record the rainfall through using a rain gauge, and we also, the next step is to determine what is the area commanded by each of these rain gauges, right? And for this could be determined by the Thiessen method. And what are the steps in that? So what we do is we first join all the different neighboring rain gauges using lines, right? So this is the first step. Step 2 is we draw perpendicular bisectors, like for example, this is the line that has been joined between these two stations, and then we draw a perpendicular bisector for this particular lines. And if I do this for this, for these 2 points like this, and for between these 2 points like this, and between these 2 points like this, and similarly between these 2 points like this, we end up with a polygon. And this polygon's area is multiplied with the rainfall that has happened in this particular weather station, recorded in this particular weather station, and that gives us the total rainfall in this particular area. And when we do it for all the different polygons that has been formed around each of the weather station, we get the total volume of water that has been collected, or the total amount of water that has been collected because of rain in this particular catchment. And then if we want to average determine the average rainfall in this particular catchment, we divide it by the overall area, we determine the average rainfall intensity, right, for this particular catchment. Or if we can just measure the total volume of rainfall that has happened in this particular area, and based on that we can determine what sort of infrastructure is required and so on. So this is the Thiessen method for determining average rainfall, and this is one of the methods which are used, which is used not only just for measuring this kind of rainfall, but it could be measured for many other things, wherever we need to assign areas to particular points and to divide an area into polygons. So why is rainfall records important? Why do we measure rainfall? Why do we keep these records? Because rainfall varies daily, monthly, yearly, and if we don't keep this record, then we don't know the kind of trends during different seasons. We don't know what happens during what could be the ranges of this particular rainfall intensities and so on. So that's why we keep them we keep those records. We also need to determine which are the drought periods. Like whenever the rainfall is 60 to 70% of the average rainfall, we call it a drought period, right? So if we keep the records, we are also able to tell when was the period of drought. And as you understand that because of climate change, India is looking at severe droughts in the coming years, right? So that means we need to keep a record. We need to see if there is a cycle of droughts. That means at certain intervals droughts are returning, or we need to predict droughts so that we would be prepared for it, right? So that's why we need to keep rainfall records. So what are the kind of data we keep? One is mean rainfall, that is the average rainfall that we were just discussing. So using this, we would be able to determine what is the total water available for a particular area. We also need to understand the duration of drought and dry periods, because if we know that the drought will be there for a 1 year period, then we will determine the reservoir capacity or the storage capacity for water, and then accordingly create our infrastructure. or we also need to understand the maximum intensity of rainfall. Why? Because maximum intensity means a rainfall event happened where the intensity was pretty high, and based on that we have to determine our drainage channels and so on. So, we have to determine the runoffs, so and design the infrastructure so that it does not cause floods, because floods cost a lot of money and also lives. So, that is why we need to record this kind of data sets in regards to rainfall. So, there are also a relationship between rainfall intensity, duration, and frequency, and this relationship is this relationship is a little bit complex. But there are some general trends, of course. For example, greater the intensity, lower is the duration of rainfall. So, that is more or less in most cases we have seen like that. So, if you have a very intense rainfall, usually it is of lower duration. High intensity storm usually have lower frequency, and both frequency and intensity of rainfall can be predicted. So, these are the different things that we need to, these are some of the trends, but there are always variations to that as well. And in India, we usually get an average annual rainfall of around 120 centimeters. So, this is not uniform in all over India. Some places it is more, some places it is less. So, average rainfall in India is around 120 centimeter per year. That means, per year we receive this amount of rainfall. So, similar to measuring rainfall, we can also measure runoff. We have to measure runoff, because that determines what kind of infrastructure we will actually construct, and how it is measured. Usually runoff is considered as the total quantity of water which reaches the stream either as surface runoff or base flow, that means subsurface or underground flow, and both of this together is known as runoff. So, that means when the water reaches a stream, then we can actually measure what quantum of water is coming either from surface flow or from the base flow. So, together they are the runoff. So, yield of a drainage basin and runoff, these are two different terms that we use. Sometimes they overlap, sometimes we use them in ways where we sometimes interchangeably, but the problem is these two are two different terms. For example, when we talk about runoff, it is instantaneous or average rate of flow given in cubic meters per second. So, that means usually after a rainfall we can say that runoff is, what is the runoff? So, that means we will express that in cubic meters per second, and that actually refers to that flow during that particular period. But whenever we say yield of a drainage basin, that means which refers to the total volume of water flowing per year from that particular drainage basin. So, that is where we actually have the entire catchment. We know the annual rainfall, average annual rainfall for that particular catchment, or we have multiple weather stations. We use Thyssen method to also multiply the polygons for each of those stations and determine the total volume of water flowing from that particular catchment. So, that is given in million cubic meters per year. So, this is yield of a drainage basin and the other is runoff, right. So, but in both cases the unit is cubic meters divided by time. So, depending on what time, one is for year, another is for second, we would call it a runoff or a yield for a particular drainage basin. Now, what are the factors affecting runoff? As you can understand that we were discussing that the water that falls on the ground, some of it goes below and then it flows below the surface, and then so that means it is not only the kind of amount of rainfall, it is also the slope of that area, what kind of soil is there in the area, what kind of other things like what kind of land use is there in the area, which actually determines what amount will go below, what amount it will flow on the surface, right. So, all these things factors in while determining the runoff or affects that kind of runoff that is generated for a particular area. So, area, slope and shape of catchment. So, these are the first things that determines the kind of runoff that is generated. Then the soil type, depending on what kind of soil, the infiltration will be determined. Then obstructions, that is the land use and land cover over there. So, depending on that we also determine runoff. Then initial state with respect to wetness. So, that means if the area is already receiving a lot of rainfall, so a new rainfall event happens. So, not too much amount of water will be able to infiltrate, because the the pores in the soil are already filled with water, so infiltration should be low, right? And the other is intensity and duration of rainfall. If intensity of rainfall is pretty high and the duration is low, so immediately you see most of the water goes off at runoff, as runoff. But if the intensity is low and it goes on for a longer period, maybe more water percolates inside the or infiltrates inside the ground. Then number of size of ditches, number of ditches that are there in that area, and then atmospheric temperature, humidity and pressure, which determines some amount of evaporation loss, and all these things are depends on that this temperature and so on. So these are the different factors which affect runoff, and these factors result in certain kinds of losses, you can say. So first is the evaporation loss, the amount of water that is evaporated from the surface itself. Then the percolation loss, that is the amount of water which goes below the ground and becomes groundwater eventually. And so something we can assume something around 25%, but it varies of course. And then there is absorption loss. This is by the plants. That means the plants will take away some of the waters, and then eventually they will let it out by evaporation or transpiration. And then this is the absorption loss by plants. So how do I determine runoff? So runoff could be determined in many ways, and usually we see lot of based on all the different factors, the kind of runoff will vary. But the most authentic or easiest way to determine runoff is to determine it by the cross section velocity method. Now what it means? It determines it based on the total quantity of water that reaches a stream at a particular point. We can measure the total amount of runoff that happens in that particular catchment, right? So we understand that there is a stream originating from a catchment, and if we can measure that, okay, how much water is already there in that particular stream coming from beyond this catchment area, first we have to know that, or this stream originates in that catchment. We just have this if we can measure the flow of water in the stream, it is basically the runoff coming from the surrounding areas which falls into the catchment, and then both by surface flow and subsurface flow, and that we can determine as the runoff. So how do we do that? So to do that, the first job is to understand what is the profile of this particular stream. So we need to determine the cross section of the stream, and it is plotted using like this is the cross section of the stream, and it is plotted using levels at different points where runoff is measured. So we have to measure the the levels of this cross section of this, the depth of this particular stream, and at different locations, and that actually helps us to determine the depth, and this gives us a cross section. And then we measure the high flood line. This is the high flood line, this is the maximum water level. So this is the high flood line, and then we divide this entire cross section into different zones using a cable. We draw a cable and we stretch it and we fix it, and then at equal intervals of the cable we extend that into in this way, and we get equal divisions in the cross section, right? And now that we have got equal division, we have got the depth of each of these divisions based, because we had the height, we can calculate the area of each of these particular divisions. And because it's a if in case of very large streams, we assume that the corners also are squares, but in case of very small streams, we can take them as a triangle, and also we can measure their area as well. So with an area of each part is calculated, and the mean velocity of water for each part is calculated using a surface float or current meter. So this is the next step. That means for each of these zones or each of these sections, we determine what is the velocity of water in this section, because we know that velocity varies at different parts of the river. That means at the sides the velocity is different compared to the center of the river, right, or the center of the stream. So we measure velocity for each of these particular sections, and then we multiply. And how do we measure that? We can either use a current meter. When we put that current meter, we would get the flow over there, or we can use something like a float, where we can have stretch two of these cables at a 30 meters or some at interval. We can let a float at one end and see at what time it reaches the other end, and depending on that we can determine the velocity, right? So once we know the velocity of each of these sections, we multiply with the area of each of these sections, and we can get the total discharge in cubic meters in second for this particular stream. So, A is the area of section, each section in square meters, V is the velocity of water in meters per second for each of this section. We just multiply both of them and then we add up for all the sections, we get the total discharge for this particular stream, which is nothing but the runoff for this particular catchment. So, this is one method. So, this is as you can understand, in this method it is a bit crude, in the sense it is not always there is a stream in that particular catchment, and not always it is easy to measure this kind of it is not easy to measure this. So, instead there are some other methods as well, and usually several researchers have developed several methods, and most of these methods, and because as we have discussed that runoff depends on the local characteristics of that particular catchment, starting from soil type, land use type, depending on the kind of slope of that catchment. So, many researchers have developed several empirical formulas which are restricted to the zone for which the formula has been developed. So, that means each of these researchers have developed certain equations through which you can measure runoff, but it is specific to that particular area, but it cannot be applied to another area. But there is one method which is the rational method, which more or less is to some extent which could be utilized in many areas, in different areas, and which is given as the total discharge, or Q is given as C into I into A divided by 360, which is sometimes called CIA by 360, and where C is basically the coefficient of runoff, I is the intensity of rainfall in millimeter per hour, and A is the drainage area in hectares. So, that means we have the area, we multiply it with the intensity of rainfall, that is millimeter per hour of rainfall, as we were doing it in the Thiessen method. So, this gives us the total volume, and then we divide by time. Time is per, this one is given in hours, and but when we determine the volume, the discharge, we determine in second. So, that is why we divide it by 3600, because we have to convert hour to seconds, and this 1 by 1000 is because we are converting millimeter into meter cube. So, that is why it is converted, this is in millimeter, we have to convert by, that is why we are dividing by 1000, and then drainage area is in hectares, which is 10 to the power 4 meter square. So, in that way that is why we end up with meter cube, and these are the factors which are going into this particular equation. 10 to the power 4 goes to the top, divided by 1000 divided by 3600. So, in this way we end up with this CIA divided by 360, right. So, this is the equation that we use, and as you can understand, we can change the coefficient of runoff to determine on which surface this particular rainfall event is happening, and based on that we can determine the runoff for that particular surface or that kind of surface. Now, let us see the values of C. Like for forest and wooded areas, it is around 0.01 to 0.2, which is determines the amount of that rainfall that either gets into the soil and the other kinds of losses, right. For open grounds and unpaved streets, it is 0.1 to 0.3. For parks, lawns and garden, 0.1 to 0.25. Gravel roads and walk, 0.15 to 13. Macadam roadways, 0.25 to 0.6. Impervious stones, bricks and blocks, 0.4 to 0.5, and so on. So, as you can understand, the more impervious the surface is, higher is the runoff coefficient. For example, asphalt, this asphalt concrete, of course, there it is around this 0.85 to 0.9, whereas roof surfaces are almost like 0.95, or you can even ignore that, because roof surfaces usually drain to the surface drains or to the drainage network, right. So, it actually does not create much of any runoff until unless there is no rainwater pipes, or the rainwater pipe is not drained is not fitted to a drainage network, right. So, in that case we can assume that. So, that means most of the runoff over here is actually we generate the entire runoff, that is 95% becomes, it cannot go inside this, it cannot percolate, the rest is generated as the volume of water that is that could be generated. Whereas for this other places like forest and wooded area, most of it goes into the ground, and only a little bit is left which is comes as runoff, right. So, that is how we can determine the runoff for a particular area. Now, let us look at a problem. A real estate project on a 13 hectare site contains 10 high-rise apartment buildings, each with ground coverage of 3% of the site area. So, that means 10 high-rise building, each with 3 means 30% is rooftops, right. And houses are residential population of 20,000. 40% of the site area is for landscape gardens and parks. So, 40% is landscape garden and parks. So, coefficient should be for this kind of surfaces. The rest of the area is roads and open parking, where the coefficients will vary, right. The site experienced rainfall of 1580 millimeter annually. Make necessary assumptions while making necessary assumptions, determine the surface runoff from the site after a heavy rainfall of 110 millimeter in 2 hours. Lot of information is given, but maybe we don't need to all the information when we need to determine the surface runoff from this site after a heavy rainfall of 110 millimeter in 2 hours. So, how do we solve that? Let us see. So, first of all, we find the total built up area is 10 into 0.03 into 13 hectares, which comes to around 3.9 hectares, and this we can assume that roof water is diverted to municipal drains directly. So, it is doesn't create any kind of surface runoff. Second is the landscape area, which is 40% of 13 hectares, which comes to around 5.2 hectares, and then areas for roads and parking, which comes to, when we subtract both of this from 13, we get 3.9 hectares. So, both of this contributes to surface runoff. So, this is our first assumption. Then we, using this rational formula, we can put all the figures in this equation CIA by 360, where we can find for landscape area where the coefficient is 0.15, and we multiply with the intensity of rainfall, which is 110 in 2 hours. So, 110 in 2 hours is basically 55 millimeter per hour. So, that is why we have put 55 multiplied by 5.2, which is the total area in hectares, and we get 0.12 meter cube per second. And surface runoff from roads and paved area, everything is same except the coefficient is different, and of course, the area is different, and this 0.65 is the coefficient for roads and paved area, and we get a total runoff of 0.39 meter cube per second. So, total surface runoff comes to around 0.51 meter cube per second. So, that means, if we have to design a drainage channel that or a storage area, we have to design a storage area which can take this kind of flow that is generated in that particular site. But as we will discuss in later lectures, that designing a drainage channel is not that simple. It is not based on the overall values of runoff that is generated or the average flow that we are getting it, but usually it is depends on many other things. So, we will discuss that later. So, roughly we can say this is the total volume of runoff per second that is generated from this particular site. So, to conclude, from this particular lecture, only part of the rainfall reaches ground in urban areas. So, that is what we just saw in this particular problem. High intensity rainfall may not result in high discharge. So, we said that high intensity rainfall may be for a shorter duration. So, it may not result in very high discharge. Rainfall records are kept, they are required for designing infrastructure, required for urban water supply, drainage and sewerage. And finally, runoff is rainfall minus the losses. So, these are the references, these are two textbooks which we will be following throughout the course, and in addition to other materials as well. So, this you can follow. So, that is the end of this lecture. Thank you.